Okay. So last lecture we looked at uniform continuity, and that's a really important concept. Today, though, we're gonna do nothing related to uniform continuity. This is just we could have done this lecture earlier, but we didn't. Okay. So, one second. Oh, okay. So we could have done this lecture earlier. And the whole idea is we're going to talk about strictly increasing functions. Okay, these are functions that satisfy whenever x1 is less than x2, then f of x1 is less than f of x2. That's the definition of a strictly increasing function. Okay, we could analogously define a strictly decreasing function. Or we could define, if we wanted to, weakly increasing and weakly decreasing functions. Okay, but our theorems today are about strictly increasing functions. Okay. And I hope it's obvious that any theorem we prove about strictly increasing functions, the analogous theorem will be true for strictly decreasing functions. Okay. So a function is monotone if it's one or the other. Well, strictly monotone, I guess we have to say. Strictly increasing or strictly decreasing. Okay, so all of our theorems are going to apply to strictly monotone functions, even though we'll just state them and prove them for increasing. Okay, the first thing to notice is that being monotone does not mean you're continuous. So monotone does not imply continuity. Okay, anyone have an example for that?
You can just take a piecewise function that increases, or I guess not piecewise, you want.
A piecewise
Floor
works.
function?
Something like this. Yeah, floor, anything.
Yeah.
Now it looks like I've illustrated that function. This or that. Okay. Anything like that. Okay? So just strictly increasing doesn't mean anything about continuity. But we are interested in when you are strictly increasing and you are continuous. Okay? So let's do our setup here. Is that I is some interval and f maps I to R is strictly increasing. Oh, I'm sorry. We said some. I have to go back. We said something wrong. Okay. Both of these functions are bad examples of strictly increasing because they're not. The floor function is not strictly increasing. It's weakly increasing. Okay. Oh, yes, it's weakly increasing. And the function I drew is also weakly increasing. So let me draw a better one. There we go. Okay, that's strictly increasing.
So the difference is the equality. I was gonna ask what it meant to be strictly or strictly monotone.
Yeah, and I'm sorry I messed it up. Strictly means that yes, when your x values increase, your y values also have to increase. Not weakly. Okay. So, here's a picture of one. Um, if you want to define one algebraically, you'll do it piecewise probably, right? X for, let's say, x up to 1, and then like x plus 2. For x greater than 1. Okay. Yeah, Benjamin writes in the chat that I said monotone, which is weakly increasing. Yeah, maybe I said that, but I wanted a strictly increasing function because that's what our theorem is about. Okay. And the whole reason our theorem is about strictly increasing functions is that then they're injective. Okay, remember injective is the fancy word for one-to-one. That's a simple exercise to prove. If you think about it, if we had f of x1 equals f of x2, okay, then how could that happen if x1 and x2 were not the same? One of them would have to be less than the other, but then the definition of strictly increasing says that says that one of the f values has to be less than the other f value. Okay? Now, once you've got an injective function, what can we say about injective functions? Any volunteers?
May I?
Yeah.
So if I recall, if for a function to be injective, if f of x of 1 is not equal to f of x of 2, then x of 1 is not equal to x of 2, correct?
Right.
Do we get inverse?
Exactly.
So we already talked about that. If we're strictly increasing, we have to be injective because we satisfy the definition. And then Daniel had what I was fishing for, which is we have inverses.
Yeah, that's one. Yeah, that also works. It's just I'm more used to the not equal definition. So
I'm not talking about a definition. I'm talking about a consequence.
Consequence. Yeah, usually when I hear injective, I usually think more about the not equal part. So, but my statement also works, right?
I'm not talking about the definition anymore. I'm talking about a consequence of being injective.
I gotcha.
There's only one definition of injectivity. Okay. So we've got an inverse function. And so given the chapter that we're studying on continuity, the theorem that we want to prove is obvious. Right? If f is continuous and it's got an inverse, does its inverse have to be continuous?
Excuse me, Dr. Batter.
Yeah.
Don't we also have to prove that f is surjective before concluding it has an inverse?
No.
Okay.
So surjective means is the other word for onto. Okay. There is something. So you want to prove that a function is surjective if you want to show that the domain of its inverse is the entire codomain of the function. Okay, but the way I've stated the inverse here, I've stated the domain of the inverse to just be the range of the function. So every function is surjective onto its range. Right, that's kind of just a triviality. So that's the way I'm going to state things. I'm just going to say the inverse exists from the range back to the domain. Okay? But that's a good question. Okay. So, I'm really sorry that I keep messing with this camera thing on my recording. I'm worried it's only going to record this page. I don't know. I'll figure it out after the lecture. Okay, so here's our theorem. And I'll tell you what, let's give it a name, because the book does too. This is going to be the continuous inverse theorem. And in the book, this is 5.6.5, but okay. Let I be an interval. And F with domain I. Let this be continuous and strictly increasing. Then F inverse, which again it would map from the range of F back to I, exists. That we already knew, but here's the new information, that it's also continuous. Now again, you can change the hypothesis from strictly increasing to strictly decreasing. You'll get the same thing. Because you can either repeat the same proof, or you can just apply the theorem to the negative function. Okay, so the negative of a strictly increasing function will be strictly decreasing. Okay, so let's do the proof. Now, I should mention that I have skipped the entire first part of this section in the book. The first part of this section in the book is about one-sided limits. Now, we skipped one-sided limits, so I'm skipping that part as well. And therefore, the proof of this theorem in the book actually uses one-sided limits, so we're not going to follow that proof. Instead, what we're going to do is just give an epsilon delta proof. Okay. But first, we claim that the inverse is also strictly increasing. Okay. So I'm going to have to scroll up. Remember our hypotheses. F is defined on an interval, and it's continuous and strictly increasing. That's it. Okay. Suppose to the contrary, that. Okay. what would it mean to not be strictly increasing? It would mean you take two numbers. I'm going to call them y1 and y2 because they're in the domain of the inverse, so they're in the range of the function. You have y1, say, before y2, but then f inverse maps y1 to something that's greater than or equal to what it maps y2 to. Okay, that's the negation of strictly increasing. But then, since f is strictly increasing, I'm going to apply f to these 2 points. Okay. And what am I going to get? Okay. Up here, I'm just using the definition of strictly increasing. So up here, if f inverse of y1 is actually greater than f inverse of y2, then I'm going to get f of f inverse of y1 greater than f of f inverse of y2. But then I have to make this inequality weak, because if f inverse of y1 equals f inverse of y2, then when I apply f, of course, the values are going to be equal as well. Okay. Okay, so we applied strictly increasing to that inequality, and f and f inverse undo each other. Good. So that's the proof that f inverse is strictly increasing. Questions? Okay. We need f inverse to be strictly increasing for the way our proof is going to work now. So I'm going to scroll up, and now I'm going to prove the continuity. Let epsilon be given. And let's pick a point. Let's let B be a point in the range okay. We will show that f inverse is continuous at B.
Professor?
Yeah.
So we just showed that f inverse is strictly increasing, right?
Yes.
Okay, and we're going to use that fact in this part.
Yeah. Yeah. You'll see. It's gonna come up real soon. Okay. Okay. We want to show that f inverse is continuous at B. I'm going to need a name for the point that f maps to B. So suppose we know there is one. We'll call it A. So f maps A to B. So f inverse maps B back to A. Okay, now we want, we want to find a delta so that blah, 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 and then the inequality we want is this. Right, we're going to want f of x minus f, but we're doing we're proving continuity for the inverse. F inverse of, and so I guess I'll use the variable y minus F inverse of b. We want that less than epsilon for y minus b less than delta. This is after we pick delta. Okay. This, I should have kind of maybe written this in a different color. This isn't a thing you would normally put in your proof, but this is just me explaining where we're going with the proof. Okay. So we want to find a delta so that if y and b are within delta, within distance delta, then the images under F inverse are within epsilon. Okay. Now, why did we do strictly increasing? We did strictly increasing because, let's say this is our point B, and I'm going to plot F inverse, okay? F inverse is strictly increasing. So if I go over here to like B minus delta, if I go over here to B plus delta, what does F inverse look like in this region? Well, it's strictly increasing. Okay. So now we want to get, here's F inverse of B. We want to choose delta so that we're within epsilon. So let's say that's F inverse of B plus epsilon. And this is F inverse of B minus epsilon.
Professor,
Yes.
what if B minus delta or B plus delta is outside of the domain of F inverse?
Well, we haven't picked delta yet. You can
We can always pick one, right?
you can just make
So,
delta
like, if
smaller.
B's at the edge point of your domain.
Mm-hmm. So you can always make delta smaller if B is literally an endpoint. And then that, that's fine as far as the proof goes, but you have to add a thing. Okay? Well, I'll try and say something about that. Right now we're just doing the intuition, okay?
Excuse me?
Yeah.
I think if B plus delta was outside because B is an endpoint, wouldn't it just be vacuously true?
Yeah. Well, and again, we get to pick delta. So as long as B isn't an endpoint, I'm gonna just shrink delta. Okay. So let's see after the proof where if B was an endpoint where we had problems. Okay, but here's the point of strictly increasing. We know that when we look at this function F inverse from B minus delta to B plus delta, we know that all the function values are between whatever it is at B minus delta and whatever it is at B plus delta. Okay. Because it's strictly increasing, so it's not like it's going up and then down, or going down and then up. It's just going between those two values. Okay? So, in the interest of time, I'm going to jump to the definition of delta, but it comes out of this picture. Okay? Okay. So the point is, ignore the 1/2 for a moment. Not actually sure if we actually need the 1/2. We'll see later. But the real point is that we want delta to be smaller than the difference between f of a plus epsilon, remember epsilon was given to us, and a, and the difference between f of a and f of a, oops, and that should be a minus epsilon in there. Okay. Okay. Now let's see what that does for us. Because delta is less than f of a plus epsilon. Oh, and by the way, both of those quantities in the minimum are positive because f itself is strictly increasing. Okay. Because delta is less than f of a plus epsilon minus f of a, that means that f of a plus delta is less than f of a plus epsilon. Okay. I just took this is clearly a true fact, right? You replace delta by what it's less than, which is f of a plus epsilon minus f of a. You get f of a plus epsilon. Now, f inverse is strictly increasing. What does that mean? So f inverse of the left is less than f inverse of the right. But f inverse undoes f. So f inverse of f of a plus delta is less than a plus epsilon. But really what we wanted is actually with the a's and with the a's replaced with b's. Okay, so remember f of a is equal to b. So what are we saying here? F inverse of b plus delta is less than f inverse of b plus epsilon. Yeah, let's scroll up to the
Wait.
picture and see if we succeeded. Yeah, go ahead.
Could you clarify how we get that IE, like how we get to how we did that?
Well, f of a equals b, so f inverse of b equals a. Just make those substitutions.
Gotcha.
Right?
The preceding statement follows from f inverse being strictly increasing?
Yes. So now let me go to the picture here and show you how this relates to the picture that we drew. Okay, this b is really, like we just said it down there, that's f inverse of a. This f inverse of p plus epsilon, that's really a plus epsilon. And here this is a minus epsilon. Okay, this is a plot of f inverse. Now, we've defined delta so that we go over here on the right, and what have we shown? We said f inverse of b plus delta, that is indeed that image, the point that I've marked on the graph, that is less than f inverse of b plus epsilon. That's exactly what we wanted, right? Okay. Now, similarly, we get the other side. So I'll just skip the math there because delta is less than f of a minus f of a minus epsilon. We get f inverse of b minus delta is less than f inverse of b minus epsilon. Greater than. Now we're going to use strictly increasing one more time. If y is any point within distance delta of b, then what do we have? We have that f of y is bounded, sorry, f inverse of y is bounded above by f inverse of b plus delta and bounded below by f inverse of b minus delta. Okay. So now if we look at f inverse of y minus f inverse of b, okay, on the right hand side, if you took f inverse of b plus delta, you would see, and you subtract an f inverse of b, the inequality we showed above, right there, says that this is less than epsilon. And then the inequality that we got on the other side says that this quantity is greater than minus epsilon. So the difference between f inverse of y and f inverse of b is bounded between minus epsilon and epsilon. That's exactly what we wanted. That translates into the absolute value inequality.
Could you scroll back up to the picture again, please?
Yes.
So, from what I understand, what we're doing with this delta is we're kind of saying f is continuous and we get the two sort of, the epsilon deltas that get really close.
Mm-hmm.
So you're trying to find a way to make the deltas for the f inverse using the epsilon from the original one, because that can get really small. Like, that's how I think about it in my head, like an intuitive thing.
Mm-hmm.
So that's kind of what we're doing here.
So, it won't let me rotate mine. That'd be cool if I could rotate the whiteboard for this. Although, really what I want is a gesture that lets me reflect the image, right? We're using the fact that we know all the values of f to say, essentially, if you look at the graph of f, I should have given this some curves, but okay. Here's f, and here's a, and here's b. Okay, this is f, and that's f of a, equals b. Okay, we're saying we want our images to be within epsilon. We'll just go look. We want the images of the inverse to be within epsilon. So we're saying go look at a plus epsilon and a minus epsilon. And that's essentially what our definition is doing. Okay, that is our definition of delta. Look how much it's changed, how much the function changed when we went from f of a to f of a plus epsilon, and how much it changed when we went from f of a minus epsilon to f of a.
I have a second question.
Mm-hmm.
Where, aside from making, aside from, well, I don't even know if I use it. Where did we use that f was continuous?
That's a really good question.
Yeah, because then any old inverse seems like it should be continuous too.
That's not true.
Right. I feel like it's somewhere in the blue picture you've drawn that shows like the existence of that epsilon spacing or something like that. That's where I feel like it should belong. It's like it exists over here, so it exists over here.
Yeah, I'm just thinking here. Okay. It's a really good question, and I wish I had thought about that when I was thinking about this lecture beforehand. Here's the thing. Think about a non-continuous strictly increasing function, okay? What are we going to do? We're going to do just a linear, and then we'll jump. Do some more linear, okay? So I'm gonna, that's 1, that's 1, that's 2, this is 2, there's 3, okay? So this is f of x equals x up to 1, and then it equals x plus 1 onward, okay? Now think about the inverse of that. What does the inverse look like? 1, 2, 3. Okay? F inverse from 0 to 1 is just linear. Okay. F inverse from 1 to 2 does not exist. And then F inverse from 2 onwards exists. Okay. That function is continuous. Okay, it's continuous on its domain. Does that make sense? So F inverse here, if the top one is F and the lower one is F inverse is continuous on its domain.
That makes sense.
So, where have we used it continuity in the proof? It's implicit in the fact that we're assuming that the range of f is an interval. In this case, in our non-continuous example, the range of f was not an interval. Okay. So,
But we do have that this inverse here is continuous, but we need a separate proof to show that.
yeah, we have this image is continuous on its domain.
Right. So, yeah, I'm just a little confused here because you have this point of discontinuity, and then, but this inverse is continuous. At
Mm-hmm.
I don't know. It just kind of it doesn't feel right. So I feel like I'm missing something.
So the real reason for this hypothesis is that really what we want to talk about are we want to talk about functions that have inverses that are defined on all of R or on all of the positive real numbers. Okay. So we could be a little bit more careful, and we could say that yes, if you're strictly increasing, then your inverse is continuous on your domain. On its domain. Okay.
So
the reason for the continuity is that then the domain of the inverse is literally an interval, and that comes out of things we proved about f mapping intervals to intervals.
So we don't particularly need that f be continuous for the inverse to be continuous on the image of f.
Right.
Okay.
You certainly don't need it, no.
Okay.
Benjamin, did you think you had a thought about where we use continuity?
Yeah, so it follows with what you said. In the proof, we use the fact that f inverse of b plus delta is defined, and that only works if the domain of the inverse is an interval, because otherwise we don't know if f of inverse of b plus delta is defined.
Very good. Very good. Thank you. Thank you. Let's just go over that real quick. Yeah. These guys. You don't know that they exist unless you know that f is continuous, because when f is continuous, its image is an interval. Okay? Where do we have these guys? Oh, yeah. Okay.
So I'm still a bit confused. Maybe this is something not to worry about, but like on the ends of the intervals, how do we show that it's still continuous?
Yeah, so you get to, okay, if you want to consider an end of an interval, okay, I think you have to give it, I think you would really, so again, this proof I gave gives you the idea of the proof. It's not a great proof. But at the end of the interval, at the end of an interval, it's actually easier to be continuous because you only have to worry about coming at it from one side. And so if one of these doesn't exist, if one of these two things does not exist, then you actually only have to worry about the other one. And the proof will go through.
Can you explain one more time about how the continuity shows the existence of those red circled things?
Well, yeah. As long as you don't pry too much into the proof. So this is if B is not at the end of the endpoint of the interval, and if delta is small enough, then these things exist. Okay.
So it's because b plus delta is an element of the image of f?
Yeah.
Okay, I see now.
Yeah.
Okay, and then if the image wasn't in an interval, we can't guarantee that those exist. Okay. That
Yeah,
makes sense.
you look at it here, and if you're looking at the point 1.
Right then.
Well, okay, f inverse isn't defined at 1. If you're looking at the point 2, right, f inverse of 2 minus delta would be over here. And it wouldn't exist.
Okay.
But,
Okay, I think that makes sense now.
okay. Good. Now I have 2 minutes. I did not think that proof was going to take quite that long. I'll state a couple theorems. Here's a theorem. If f is continuous and injective, then it must be strictly increasing or strictly decreasing. So our previous theorem said if you are strictly increasing and continuous, then your inverse is continuous. You might wonder, what about the inverse of functions that aren't strictly increasing? Continuous functions that aren't strictly increasing. And this theorem says if you've got an inverse, remember injective is saying you've got an inverse, and you're continuous, then that previous theorem must apply, because you must be either strictly increasing or strictly decreasing. Okay, I'll leave the proof to you. It's the intermediate value theorem. Okay. Now, in my remaining minute, I just want to note that this is how we define nth roots, or this is one way to define nth roots. So we know, if we look at the function f of x, that sends x to the n, for a natural number n, we can prove that's a strictly increasing function. There have been homework problems to that effect. And we've proved it's continuous. Okay. So we know it's got an inverse, and what we just proved shows that the inverse is continuous. Okay. So f inverse of x, which we denote by x to the 1 over n, is continuous. Okay. We want to be a little bit careful when we're dealing with even, so you should look at the book, but there's nothing too deep here. When n is an even integer, you want to be a little bit careful to restrict, you restrict the domain of f to only be the non-negative real numbers. Okay? This is our standard restriction on square root. Okay? When n is odd, everything goes through a little bit easier. It's all fine. Let me just leave you with this definition now. If we want rational powers, that would mean that we have two natural numbers. We define x to the m over n to be the nth root of x to the m. Okay. That would be positive rationals. What about negative rationals? And I should say, we do want x to be positive here. Unless we really want to get concerned about m and n. Okay, we can define this to be x to the 1 over n to the minus m, which would be 1 over that to the m. Okay, so we get that the inverse of the power function is continuous from the theorem we just did. And then we define these fractional powers. Since those are expressed as compositions of continuous functions, those are also continuous functions. Okay. Now, I want to leave you with two more things. Here's a theorem now. Given the above statements, you have that x to the m over n is x to the m to the 1 over n. That now becomes a theorem that you have to prove, but the proof is not hard. Okay. And now my final question would be, how would we define x to the y? How would you define an arbitrary real power of x?
Is this like a rhetorical question or a question?
For now, it's a rhetorical question.
Okay. All right, I'll save my
but,
idea.
But yeah, you might want to think about how we're going to define it.
A broad guess is a limit.
Yeah, you're right. But then, how would we know it's a continuous function?
That's interesting.
Right. Don't we use integrals? Well, you can't get it with an integral because that's the integral of another function that's x to some non-rational power. Okay. I just this morning put up, well, that's the end of